All right, let's talk about one of those LeetCode problems that looks super intimidating at first glance. Today, we are cracking string with concatenation of all words. And trust me, by the end of this, we're going to turn this challenge from something daunting into something you totally get.
So here's how we're going to tackle it. First up, we'll decode what the puzzle is even asking for. Then, we'll get into the core idea, which involves two key tools, sliding windows and checklists. From there, we'll map out the step-by-step strategy, see it in action with a walkthrough, and finally, we'll wrap it all up with the performance analysis and the big takeaways. First things first, before we can even think about an algorithm, we have to be absolutely crystal clear on what we're trying to achieve. Getting this part right is half the battle.
So the problem talks about a concatenated substring. What on earth is that? Well, it's a chunk of the main string that's made up of all the words from our list, used exactly once and smashed together with no gaps in between. The order of the words doesn't matter, but they all have to be there.
Okay, let's make this real. Imagine you've got this string, barfoot the foo bar man, and your target words are foo and bar. Your job is to find the starting index of any substring that's a perfect combination of foo and bar. So you're looking for either foo bar or bar foo hidden inside that longer string. Now your first instinct might be to just, try everything. Check every single possible starting point, generate all permutations of the words, but let me stop you right there. For a hard problem, that brute force approach is a one-way ticket to a time limit exceeded error. We need a much smarter way to do this.
So if brute force is out, what's the elegant solution? Well, it comes down to combining two really powerful computer science concepts. These are the tools that will let us solve this efficiently.
First up, we've got the sliding window. Just picture a frame that's the exact length of all our target words put together. We're going to slide this frame, or window, across the string and only ever look at the chunk of text that's currently inside it. It's a fantastic way to break a big problem into small, manageable pieces.
And to go with our window, we need a way to keep track of things super fast. And for that, we bring in the hash table. I like to think of it as our brain for this problem, or more simply, a checklist. It lets us instantly answer questions like, have I seen this word before? And is this a word I even care about? That speed is absolutely crucial.
All right, we've got our window and we've got our checklist. Now, how do we actually put them together to build our solution? Let's walk through the high-level game plan.
The logic here is actually pretty intuitive when you break it down into these 5 steps. First, we prepare by building that master checklist of all the words we need. Then we start to slide our window across the string. For every position of the window, we track the words we see inside it using a second checklist. And here's the key. We constantly validate. If our window's checklist ever perfectly matches the master checklist, boom, we've found an answer. If things don't match up, we just adjust our window and keep on sliding.
Okay, enough talk. Let's actually see this thing in action. Theory is one thing, but watching the algorithm run on our example is where it all really clicks.
So, the very first thing we do is look at our input words, foo, bar. We build our master checklist from that. It's simple. Our goal is to find a window that contains exactly one foo and one bar. This is our target.
All right, the process begins. We place our window at the very start of the string, at index 0. It looks at the first word, which is bar. Hey, that's on our list. So we make a note in our window's checklist. Okay, I've seen one bar.
Now we don't restart. We just slide our window over to include the next word, which is foo. Is that on our master list? Yep, so we add that to our window's checklist. Now if you look at what's covered by our window, the string bar foo, our checklist says we've seen one bar and one foo.
And what do you know? We take a look at our Windows checklist and compare it to our master checklist. They're a perfect match. That means we found a valid concatenation. So we record the starting index of our window, which was 0, as one of our answers.
Okay, this next part is super important. It's how the algorithm handles failure efficiently. As we keep sliding along, our window eventually encounters the word the. Now, the is not on our master list at all, so what do? We don't just move on by one character. We know this entire window is invalid, so we blow it up and completely reset our search, jumping our starting point all the way past this invalid word. This is a huge optimization.
All right, so after that reset, our algorithm keeps scanning. Eventually, it starts a fresh window way down at index 9. The first word it sees is foo. We're back in business. We add foo to our brand new window checklist. And just like before, the window slides to grab the next word, bar. We tick that off on our Windows list. So now, our current Windows checklist once again contains exactly what we're looking for: 1 foo and 1 bar. And boom! We do our check, and it's another perfect match with our master list. So we've found our second answer. The starting index for this one is 9. Okay, so we've seen how it works. Let's take a step back and talk about the big picture. Why is this solution so good? And what are the main ideas you should really walk away with?
When we talk about performance, this is where this approach really shines. The time it takes is basically proportional to the length of the string we're searching. We're just making one main pass. We're not doing some crazy number of checks that explodes as the input gets bigger. And the amount of memory it uses? Just enough to store our checklists. It's incredibly efficient on both fronts.
So if you remember anything from this, remember these key points. First, sliding windows are your absolute best friend for these kinds of substring problems. They chop the problem down into bite-sized pieces. Second, hash tables give you that lightning-fast lookup speed that makes the whole thing practical. Our logic is also smart enough to handle finding a good word, a duplicate word, or a totally wrong word. And maybe, most importantly, this general pattern is something you can use again and again.
And really, that's the whole secret. That's how you can take a hard problem and break it down until it feels, well, not so hard anymore. So the final question I'll leave you with is this. Now that you have this powerful window and checklist technique in your back pocket, what other tough problems